Hello, everyone. Thank you very much for coming to Victor's talk. Today, we are hosting him from Brown University. Victor Kemmoe is a PhD student under the supervision of Anna Lisianskaya, as you know her very well from the anonymous credentials domain. And today, Victor is going to talk about merging two very difficult topics. He's going to talk about lattice-based accumulators and more specifically how to use them in the application of anonymous credentials, credential revocations. So, Victor, welcome.
Thank you for having me here. It's a pleasure to give a presentation on this recent work with both Anna and Ken. I hope people online are able to hear me. So first I will start with motivations. And the motivations here will be the case of anonymous credentials. And briefly, from a high-level point of view, how anonymous credential works is that you generally have an organization that holds a private key and a secret key. And you have a user that we are going to call Bob here that has a list of attributes. And they will go through a credential issuance phase, at the end of which Bob is going to obtain some credential from the organization. And what those credentials will enable Bob to do is that at a later date, he will be able to go to a vendor here that will hold the organization public key, and they will interact through some form of like showing protocol where, with respect to a predicate P, that will allow Bob to, in some sense, use the credential that he obtained from the organization. And more concretely, you can think of it as this predicate to be saying that Bob is over 21 years old and he can drive. And at the end of this showing protocol, what we want for the anonymous part is that the vendor here only learns that Bob's credentials satisfy the predicate P, and that's it. Right? So it doesn't necessarily learn who Bob is. All he knows is that there's a user on the other end that has credentials that satisfy P. Right? Now there's this questions on how can we revoke Bob's credentials, right? Because in the real world, credentials are revocable. A judge can issue a decision that says that Bob's credential should be revoked. For instance, if it's a driving license and Bob's is found to be guilty of driving under influence, then his driving license can be revoked for that, right? One quick fix here could be that we can include an expiration date on Bob's credentials, saying that, after December 2025, Bob's credentials should no more be accepted, right? But this is not really nice, because if he commits DUI in November, then we have to wait till December in order for his credential to no more be valid. So now what we are interested in is how can we achieve this notion of fine-grained revocation for Bob's credential. And now I'm going to present a cryptographic primitive that will allow us to do exactly this. Right? And the primitive in question is going to be a positive dynamic accumulator. And briefly, what a dynamic accumulator is, in this case positive, it's a tuple of algorithm where in the beginning you have this gen algorithm that will take the security parameters and some auxiliary information, and it will output the public parameters, a secret key, and an initial accumulator value, where that this initial accumulator value AT0 is going to represent the empty set. After that, we will have access to this algorithm add that will take the initial accumulator value, some element here x1, and what it will output is a new accumulator value, a membership witness for x1, and some update message that can be used to update other witnesses. And basically, what this accumulator AT1 here represents is just going to be this set that contains x1, right? And WX1 here, it's going to be a certificate that attests that X1 is really in the set represented by the accumulator. Okay, so we can do it this many times, and now say we have an accumulator that represents this set S here with X1 to XM and Y, right? Since it's dynamic, we will have the possibility to call this algorithm delete that will take the accumulator value representing that set, the element y that we want to delete, and its membership witness, produce a new accumulator value, some update information, and now the accumulator value that we will get at the end of delete will represent this set S without the element y, right? And in addition to these three algorithms, we will have two other ones, mem with up, that will be the algorithm that anyone can call to update the membership witness with respect to the most current value of the accumulator, and also the mem verify that will help us verify that X is in the set represented by the accumulator given the actual accumulator value and the membership witness for X, right? And in terms of other conditions, we will want compactness in the sense that the size of the accumulator only depends on the security parameters. And also for the membership witness of X, to make things non-trivial, we will want the size of the membership witness to depend on the security parameters and the size of the element X that it represents. In terms of security, at a high level, what we will want is that it should be hard for any polytime adversary to produce a membership witness for an element X that's not in the set represented by the accumulator. And we will have this last condition that's not always included, but that will be nice for the application of anonymous credential here, which will be communication efficiency, which basically states that the size of this update messages that's produced during all these operations only grows with the number of deletions. Right? In some sense, you can view it as only producing these update messages when we perform deletions. Any question at the level of the definition?
Do you have any goals for like privacy for saying besides elements, or is that like out of scope of this?
Well, here we do not really have a notion of privacy because what we will see down the line is that the element that in the accumulator will essentially be random strings. Yeah, but you can also obtain some form of privacy by first computing a hiding, by using a hiding commitment where you will first commit to the element X through your commitment and then put the commitment inside the accumulator. Yeah. So, any other questions at this level of definition? Okay. So now we will see how accumulator can be used in our application of anonymous credentials, right? So we still have this credential issuance phase. And now when Bob receives his credential, instead of just getting his credential, he's also going to get an element X and a membership witness for X, right? And this credential that he was going to obtain will also depend on that element X, right? And now down the line, when he will want to redeem, he will still go through this shoring protocol. But now the predicate, instead of Bob simply proving that his credentials satisfy P will be augmented to be that, he also has an element X that is inside the accumulator. And this accumulator value will be public and also be held by the vendor, so that the vendor will be able to convince that Bob owns an element X that is inside the accumulator in addition to credentials that satisfy these conditions, right? Where here's the age and whether he can drive. And now how can we achieve the revocations? All we need to do is remove X from the accumulator. And now Bob will no more be able to satisfy that last conditions, which was that mem verify for X goes true, right? By removing X from the accumulator. Okay.
Does that mean that you need to prove that like under the zero knowledge proof, you need like an accumulator that's compatible with?
Yes. You need, indeed, you need an accumulator that will be able to support this mem verification has zero knowledge protocol. Yeah. Yep.
A changes every time a new credential is issued, right?
No. That will be the case that we will present here. A does not change when things are added to the system. So right, when people join in the system and your element X is added to the accumulator, the value of the accumulator will not change. It's only going to change during deletion.
Okay. So there's a fixed value for A that's just created.
Yes. In the beginning, as long as you do not perform deletion, you will not have to change that value. It's only when you will perform deletion, meaning you will remove someone from the system, that you will need to change the value of A.
So is it all the X's are kind of included by default?
No. Because here we will require that it's only the organization who is going to be in charge of managing this accumulator that will be able to add people, in the case of anonymous credential here, it's only this organization that will be able to add people inside that accumulator. And we will see why. Yeah.
No, maybe I'll wait and see. I still don't understand.
Is this set of people like known, predefined? We just don't add them, but they.
No. They come as the system
Dynamic.
run. Yeah, it's dynamic.
Not
Yeah.
necessarily.
So I already forgot from the previous slide is that soundness only holds against like an external party, not the organization. Is that right?
Yes. External party. Yes, that's a good question here. Yes, so soundness will be that, for instance, if we have another party, Alice here, Alice will not be able to generate an element Y and a membership witness for Y. But yeah, it might be possible for the organization to do that, but in this case, we are relying on the fact that the organization is trusted. Yeah. Okay. So here it's just some prior work on positive dynamic accumulator. I know it's a little bit, a lot of word annotation, but all I want you to focus on is this column for the size of the update message after additions. And what you will see in the first block is that from the strong RSA assumption and the Q-strong defillment assumption, which are both non-post-quantum assumptions, we have construction where in one case, right, the update message after add, it's kind of like this length L, and we also have other flavors where basically this update message, it's empty, right? It's kind of like nothing is produced, right? Which is kind of like this notion of communication efficiency that I previously mentioned, right? Because during add, nothing happens, so there's no need to produce an update message. And now, from the point of view of post-quantum assumptions, right, in the second block, you will see that all constructions need to issue some form of update messages after something is added inside the accumulator. And this is where we come in and we propose a construction based on post-quantum assumption. Here, the MSIS is just short integer solutions, and L-succinct MSIS is a variant of the MSIS assumptions. But yeah.
So just to clarify, these up message add and del, so these are changes for the witnesses, right? To update the witness.
Yeah, but also the okay. To be a little bit more precise, whenever an update message is produced, the accumulator value is also changed. Yeah. So they go, at least for most of those constructions, they go in tandem, right? Whenever you produce an update messages, it also changes the accumulator value. So when you do not produce, implicitly, this means that the accumulator value does not get changed. Yeah.
Do these all like, there's so many different flavors of accumulators. Are these all like the same kind of definition as you had, or like they're just?
Oh,
like
yeah, no.
Everything that's out there.
Yes, here I only focused on positive dynamic accumulator, where you have this membership. But yeah, you definitely have other flavors, and yeah, here it's all that's on this table are those that satisfies this notion of positive dynamic accumulator. That's it. Yeah. So for the rest of this talk, I'm going to present our construction in the first row, which is based on the module short integer solution, which is kind of like a variant of the short integer solution, which is an assumption that's believed to be post-quantum. Okay. But before doing that, I'll just want to remind the audience of the notion of digital signature because they're going to be useful for our construction. And basically, the digital signatures, this triplet of algorithm where you have a gen, sign, and verify, where gen gives you your public key and secret key. The secret key allows you to sign on a message and produce the signature sigma. And you have the verify algorithm that given the public key, the message and the signature, it will either accept by returning a 1 or reject by returning a 0. And in terms of security, from a high-level point of view, you'll want that it should be hard for an adversary to produce a message M star and sigma star given only the public key and a set of pair of valid message signature where M star is not included in that set. Right? All good here? Okay. So now, our construction from a high-level point of view can be abstracted to this type of digital signature where you first have your triplets that we saw on the previous slide, but in addition, you have an update public key algorithm and an update signature algorithm, where what the update public key is going to do is that it's going to take the public key, secret key, and then a message M bar and produce a new public key and some update information. And the update signature is going to take the message M, the signature on M, the update information, and produce a new signature. Right? And in terms of requirements, what we want is that for any message different from M bar, where M bar is the message that was used during the update of the public key, the updated signature will still verify with respect to that new public key. And in terms of, for the message M bar that was included inside this update public key algorithm, you will not be able, in some sense, you will not be able to generate a signature sigma prime on M bar such that the verification algorithm goes through with respect to the new public key. Right, so at a high level point of view, basically what update PK is doing here is that it's revoking signatures on messages, right? Now, how will this give us a positive dynamic accumulator? Simply, given now this signature, digital signature upgraded with these two new algorithms, to add an element inside the accumulator, we're just going to sign, right? And this is the nice thing here, because since we're signing, nothing changes. To delete, we are going to update the public key of the signature, right? And now, oh, by the way, the witnesses for the accumulator are going to be these signatures that we issue, right? And now, to update the membership of an element that is still inside the accumulator, all we are going to do is call this update signature to update the signature for that element, right? And the verification is still the verification of the underlying digital signature, right? And this is...
So is the public key the A value from the previous slides?
Yes. So in this case, yes, the public key for the digital signature is going to represent the accumulator value here. And this is the reason why whenever things get added, nothing changes in the system. So you do not need to perform any kind of update on those witnesses. It's only when you perform deletions.
It reminds me of this puncturable encryption, like kind of you're puncturing the secret, the keys, but the public key doesn't change. Like, is it a similar? Is the analogy correct that you keep the kind of the public key the same, but without changing it, you can continuously update the secret key based on the revocations that you are doing. Does it sound?
I guess it's a little bit similar, but for this notion of puncturable I guess, potential public key or puncturable signature. Generally, what you have is that you will puncture the secret key on a point which will prevent you from generating a signature on that point, right? So this is kind of like forward. So you are trying to generate signatures and we are preventing you from generating signatures, right? Whereas here, the signature have already been issued and we want to sort of like revoke those previously issued signatures, right? So in terms of a timeline, you can see, right, like this puncturable notion is kind of like forward, whereas ours is kind of like backward.
And you're sort of puncturing the public key, so the verification is getting points for this key, which is interesting.
Yeah. But also, I would like to note that, if you look at this prior construction based on a strong RSA assumption and the Q strong differential assumption that I previously listed in that big slides with some related work, those that allow you to add element inside the accumulator without changing the accumulator value all follow this template where at the core it's a digital signature that's upgraded to support this update PK and update SIG. Right. And this is what we're going to do here, where we are going to take an existing signature based on the short integer solution and upgrade it with this update PK and update SIG. But moving forward, I'm just going to integrate this algorithm directly in the accumulator construction. Hopefully that will be clear enough. Okay, and so as you can see from this construction, it automatically satisfies this notion of communication efficiency because you only produce these update messages whenever you perform deletion. Okay? Yeah. So now, sort of like a brief detour on some background that will be required a little bit to describe our constructions. In the lattice-based cryptography setting, we have this gadget matrix, where you can view it as just a matrix that contains powers of 2 on its diagonal and 0 everywhere, right? Like when there's this blank space, it's just going to be 0. And one of the nice things of this gadget matrix is that it admits this decomposition function, or you can view it as binary decomposition here, where given a vector, you can compute a binary decomposition of vector, and then if you multiply the binary decomposition of the vector with that matrix, you recover the vector, right? This is what stated here by having G times G minus 1 of U, right? And the other thing is, binary decomposition, so the infinity norm of that vector is just going to be 1. And the next thing is going to be this nice theorem from lattice-based cryptography, which sort of like try to condense some form of like homomorphisms on matrices. So basically, what you have here is that we have this family of Boolean functions or Boolean circuit that operates on L-bit input, and we have this nice algorithm eval f and eval fx, where what eval f does is that it will take a function from that family and a matrix B and produce a matrix BF, right? And eval fx will take the function B, an input, and produce h f of x, right? And for some class of for some families, you will have this nice property that the infinity norm of the matrix H, it's going to be 1. And what the output of eval f and eval fx will do is that they will satisfy this nice equality that says that if you take B and subtract it with x tensor the matrix G that we previously described, multiply it with this matrix H f of x, you will obtain B, the matrix BF, subtract it with the output of the function apply on x times G, right? A little bit more abstractly, you can view this B minus x tensor G as some form of like encryption of x, and this matrix H fx represent the homomorphic operations that you operate on the ciphertext, and what you get out of it is the encryption of f of x. right? And for this condition here will especially hold in the case when the function that we are going to work with are indicator functions, right? Where all functions here are just parameterized by a binary string such that it outputs 1 if the input is equal to the binary string that parameterized the function, and 0 otherwise. Okay? Any questions here? Okay. So now we're going to see how this is going to play and help us get our positive dynamic accumulator. Okay, and another detour is that, okay, yeah. So for the public parameters of our accumulator, it's going to be a matrix A, another matrix B that's going to be wider than A, and the secret key is going to be this a trapdoor for the matrix A, right? Don't really need to know what this trapdoor is, but basically it's going to allow us to execute this sample prey algorithm, where if you give the algorithm the matrix A concatenated with another matrix B bar and submatrix U, it will output a matrix V such that A concatenated with B bar, the whole thing times V, it's going to be equal to U, right? That's all the algorithm, the secret key is going to help us do. And our initial accumulator value is just going to be a random matrix, right? Now, how you add, given all these parameters and secret key, you will just execute sample prey on the matrix A concatenated with the matrix B minus X tensor G. And from the literature, with respect to the accumulator value A. And from the literature, that's just the Agrawal-Bonnet-Boyen signature that you can derive from their IBE scheme, right? Where the IBE stands for identity-based encryptions, right? So in that construction, there's a signature, and this is what we extracted to have here, right? So add is just sign with respect to that signature. Yep. I guess you.
How long? I guess it's like whatever. I'm just trying to think how big these signatures are.
Oh, here the signatures are going to be M bar, right? So it's going to be this times LM, because you have this concatenation here. And you want that when you multiply that signature with this concatenation, you get back A, where A, it's another matrix. Yeah.
So it's like M bar plus LM.
Yes. Times, you have another, I guess times M, because you need to recover matrix. But you can compress all this, right? Here I'm just presenting the matrix version, but in the paper we have a compressed version where we work with vectors, where things are a little bit shorter. It's just that with matrices it's a little bit easier to see the operations that are happening, right? Now, to delete, we're just going to take our accumulator value, the element Y that we want to remove, and we are going to use this eval F from our homomorphic operation on matrices toolkit, and it's going to produce this matrix B indicator of Y, right? And we are going to add that matrix to our accumulator. That's all we do. So we are updating the accumulator value to be A plus that. And the update message is just going to be the element Y. Now, to update, we can call this eval fx on B and X, right, to obtain H indicator Y, B, and X. And then, given now the witness of X, we can just add that matrix that contains 0 at the top and the matrix H at the bottom. And that's going to be the updated witness. And to verify, it's just going to be verification from the Agro-Bonemboyance nature, where you will check that A concatenated with B minus X tends to G times WX gives you the accumulator value, and then you also check that the norm of WX is small. Right. So at least I hope that you believe me that the verification is fine here, and I'm going to show you that actually performing deletions and membership witness update this way is still it's correct in the sense that after updating your witness, you will be able to recover the accumulator value during the verification. Okay. So how that's going to work? We have from delete, we have that our new accumulator value is going to be the old accumulator value plus this matrix B indicator of Y, right? Where Y was the element that was deleted from the accumulator. Now the new witness for our element X that's still in the accumulator is going to be its old witness plus this matrix that contains 0 at the top and the matrix H at the bottom, where the initial witness is the signature on X, right? With respect to the old accumulator value. So now all you need to do is take the matrix A concatenated with B minus X tends to G, right? And when you multiply with W X prime, after opening W X prime, it's in fact multiplying with S of X plus this matrix that contains 0 and H at the bottom. And when you distribute what's inside the parentheses, what you get is the old accumulator value plus B minus X tends to G times H, right? And from our toolkit on homomorphic operation on matrices, what this B minus X tends to G times the matrix H represent is just B indicator of Y minus indicator of Y times G, right? Applied on X, right? But because X and Y are different, then this indicator is just 0. So at the end, all you get is A plus B indicator of Y, which represent this new accumulator value, right? So, any questions here?
So the thing you guys do is there is like different for every pair of X and Y. It's like different for every X. Is that?
Yes, yes,
So
yes.
the
yes,
update
yes.
message is like a specialized update message for every.
Oh no. So going back
Sorry, I think
to
I
the
forgot.
construction,
Yeah.
all the update message is it's just going to be the element Y that was deleted, right? Because from the binary string Y, you'll be able to recompute the indicator functions for Y, and then from there, given your element, you can compute this eval f functions, eval fx function, right? So yeah, the update messages is just the element that was removed. That's it. Okay. Yeah, and the other thing is, well, you know, in the lattice setting, it's not like in group-based crypto where everything is random and you don't care about size. Here we care about size, and you will notice that during the verification procedure, we need to check that the infinity norm of Wx is small, right? But here we are performing an operation where we add these matrices, which, you know, at the end of the day, it's going to increase the norm of the witnesses. But since we are working with just indicator functions, we have that the infinity norm of this matrix H is just going to be 1. So overall, after an update, the size of the witness for X is just going to be increased by 1. So if you set your parameter, basically, if you set your parameters accordingly, you should be able to support polynomially many deletions, right? So that's the thing here. We are bounded in the norm of deletion that we can perform. Whereas for other construction from strong RSA or Q-strong defilement, there's no bound on the number of deletion that you can perform. Okay? Yeah, so now we will see a little bit about an estimate of sizes. So here it's kind of like a comparison of our construction with prior construction that are similar to ours, right? And I guess all I want you to focus on are these two rows because in some sense they represent the same type of accumulator. Well, in the first one, the accumulator that you get here is whenever you perform addition and deletions, you need to update witnesses. Whereas in our case, you only need to update witnesses during deletions. And so we set up the parameters so that we can handle 2 to the 32 deletions. And you'll see that things are approximately the same. But yeah, overall, it's still not great in the sense that you can go and directly deploy this and plug it in the real world system. So there's still some work to do there. Right. So any questions at the level of this table? Oh, and this was for security parameters of 128-bit that we got this result.
So why did you say you can't just plug it in to some systems?
Yeah, because, like, well, first, the product parameters are still big in comparison to things that you can get from RSA or Q-strong defilement over elliptic curve, right? And the witness is also kind of like big, right? Like 12 megabyte. If you will have to 12 megabyte for the prior construction and 14.72 megabyte for ours. So sometimes you will need to carry that around and update it, right? So that's what I meant by.
Is there any, so you also, like again, the zero knowledge proof, you need a zero knowledge proof that's sort of compatible with these if you wanted to use it for like credentials, right?
Yes. But the zero knowledge proof from Lattices, we already have good ones, right?
Like these kind of signature things.
Yeah, yes. But overall, the main bottleneck is the accumulator. The zero knowledge proof from prior work, when we plug them to our accumulator, we were able to get something of approximate size of 125 kilobyte. Yeah, so in terms of zero knowledge proof, things are good over there. The main issue is at the level of the accumulator, right? Where things are still not good enough. Yeah. So I guess.
So if it's really, if it's really small, does that mean that the sort of the thing you have to, the big thing here, the like megabytes, the 14 megabytes, that's just something you have to store locally, but then like what you're actually sending to the verifiers can be much smaller?
Yes.
That's interesting.
Yeah. Because you need to store these witnesses in order to be able to perform the proof, right? But the proof can be smaller. Okay, so now I will, with the remaining time, I will try to quickly sketch the security of this accumulator because there's some, subtleties that need to be taken care of, right? So, okay, the first thing is that the accumulator that we get here, it's replacement free in the sense that once you add an element X and delete it, you cannot re-add that element X. And the reason why, so suppose we have this chain of action that happens at the level of the accumulator where you add an element X, delete X, and then add X again, right? So in some sense, it means that you have this old witness WX for X and this new one, WX hat, right? And from WX, using our toolkit for homomorphic operational matrices, you can use this eval F to sort of like transition WX to WX tilde. And now with WX tilde, what you're going to get is the most current value of the accumulator minus this matrix G, where it's this matrix that contains powers of 2 on the diagonal, right? And since WX hat is a good witness, what you're going to get is the accumulator value, simply the accumulator value, right? But now, given these two witnesses, right, like WX hat and WX tilde, if you subtract them and multiply with A concatenated with B minus X tends to G, what you're going to get is the matrix G, right? And why this is bad is because this matrix G can help you forge membership for X. So this is the reason why we need this condition that if you add X and delete X, you cannot re-add it afterward, right? So now in terms of security, our accumulator, right, we will prove that it's going to be secured in this setting where this replacement-free condition holds, and it's going to be secure with respect to the short integer solution problem that I'm going to define more concretely in upcoming slides. And also, it's going to be secure with respect to this notion of selective security, where what it means is that the adversary will need to tell beforehand what element X is going to forge membership on before receiving the parameters for the construction, the public parameters for the construction, right? But we will see down the line that this issue can be fixed. Okay, so what's the short integer solutions? In brief, you have this random matrix A bar, and what the assumption says is that it should be hard to produce this non-zero vector B that has low norm, such that if you multiply A bar times V, you get 0, that for the homogeneous case, and A bar times V equal T if you're in the inhomogeneous case with respect to some other vector T that's different from 0. Right. So now you'll see that, okay, now suppose we have this adversary A, right, that tells us that he's going to produce a forgery on X star that he tells us beforehand, right? And he actually does it. So he produced a witness membership on X star. So in the case, he never queried us to add X star in the accumulator and produce the membership for X star, then this is simply because of the requirement that the WX star needs to be short, right? This is going to be a solution for the inhomogeneous case with respect to A, right? So you can view A here, or you can, in some sense, briefly, you can embed T inside the accumulator value A, and because he never queried, then he found the solution for the inhomogeneous case of the SIS solution, of the SIS problem, right? Now, in the case, he asked us to add X, right? And then because it needs to be a valid forgery, so he needed to ask us to remove X from the accumulator, right? Then what we will have, in some sense, using the idea is similar to this problem form that we had and where we needed to introduce this replacement-free condition. Basically, since he asked us to add X, right, we know that there's a witness, W X tilde, that's different from its forgery, such that when you will multiply W X tilde with A concatenated with B minus X star times G, you will get the accumulator value minus G. And then since his witness is a valid one, when you will multiply it with the same matrix, you will get the accumulator value. And by subtracting those two witnesses, you will get the matrix G. And then from the matrix G, we will be able to generate a low norm vector V that's different from 0, such that that matrix A times B minus X tilde tensor G is going to be equal to 0. And the reason why we need the selective security here is because we are going to basically use it to prepare this matrix B here, such that when you will subtract with X star, you get something nice. That's in brief. And because we are in this replacement free setting, right? Like you cannot re-add the element X that you previously removed, then these two conditions are sufficient here, right? Either you never added X, or if you added X, then you ask S to be removed, and that's it.
Like, where does this use the selective? The fact that it's just a selective attack?
to prepare B.
So it's like embedding the T in there somewhere, is that what it is?
Oh, no. It's more like, more concretely, you will receive. So we want to be able to break these SIS assumptions, and you will receive this matrix A bar, right, from your SIS challenger. And now, basically, in some sense, we are going to use the X star that the adversary is going to give us to prepare A and B, such that when you perform this operation here, you get A bar. Does that make sense? Yeah, that's why.
Or in other ways, you get something that you can generate signatures, because you still have, it's not selective. Sorry, the adversary doesn't have to tell you the other elements. Instead, it just has to tell you.
Yes. He just needs to tell us where he's going to do the forgery. That's it. He does not have to tell us the other things that he's going to add or remove from the set. Right. Okay. So now with the 5 minutes remaining, just want to quickly mention that how this condition can be fixed, right? Because replacement-free, selective security, for some application, this might seem a little bit undesirable, but there's this prior work by Baldimsi et al. Where they showed that if you have a non-adaptively secure positive dynamic accumulator, and you combine it with an adaptively secure digital signature, then you get an adaptively secure positive dynamic accumulator. Where non-adaptive here means that the adversary will need to produce all of its query before receiving the parameters, right? And here, the non-adaptive means basically the adversary will tell you what he's going to add and delete beforehand, before he gets the accumulator. It's a little bit different from the selective setting, where for selective, he just tells us where he's going to forge. Right. And more specifically, if the starting non-adaptively secure positive dynamic accumulator was communication efficient, then the resulting adaptively secure positive dynamic accumulator is also going to be communication efficient. So what we do here is that basically we show that this is enough for us, because it can also be easily adapted to the case where you have this selectively secure positive replacement free accumulator, and this gives you an adaptively secure positive dynamic accumulator. Right, so by just, if you're willing to combine an adaptively secure digital signature, you can remove these caveat that we have on our construction.
Adaptively secure digital signature, that's just a traditional.
Yes, just the general one that, yeah.
Existential unforgeability.
Yes.
Like the whole
Existential
regular-
unforgeability, yes. Okay. But I would like to note that, for the case of anonymous credential, the base construction that does not require combining with an adaptively secure digital signature is sufficient. And the reason why, it's because, going back to this picture with the anonymous credential setting, the element X that's given at the issuance of both credentials here can be randomly sampled, right? So it can be a random string. And because it's going to be a random string, it means that with low probability, we are going to add that element X in the accumulator again, right? So that's why, in some sense, this is fine. And also because it's a random string, in some sense, briefly, the reduction can sort of like guess it beforehand, right? Like the adversary does not have to necessarily tell us. Yeah. Now, as Melissa mentioned beforehand, we need to be able to have this zero knowledge protocol to be able to prove that we know an X and a membership for X, such that the membership verification goes through. And I'm just going to briefly mention that we can support it for this construction. And the reason why is because, from a long line of work on lattice-based zero knowledge proof, we know how to prove that we have knowledge of a short vector x, such that when you multiply it with a matrix C, it's going to be equal to this vector T that's going to be public, right? And for our case, it's almost similar to that, right? Where we have this matrix A concatenated with B minus x tends to G times Wx. It's going to be equal to A, where Wx is going to be short, right? But the only the difference here is that Wx, it's going to be private, but also x is going to be private, right? So if x was public, then we would have just used this prior work. But by committing to x first and through some algebraic manipulations, you can, in some sense, rewrite this expression at the top into an expression that only depends on public value that given to you from the opening of the commitment of x, right? Where this C here and then this Z of x here are part of the opening for the commitment of x. Right? And then by doing additional, algebraic manipulations, you can recover a proof, is basically a zero knowledge proof of knowledge of x and the membership witness for x, such that that initial equations 1 holds.
So which things in that bottom line are public, like known to the verifier?
These were red ones. Except of this, because this one still needs to be private. So that's why the additional algebraic manipulation comes in to be able to handle this part. Right, because y of x here needs to be private, otherwise if you reveal it, then you'll be able to recover x. Yeah. Okay, in the paper we have more information on how to handle that case. So, yeah, so that's all. Thank you. Yeah. Any more questions?
I don't see any questions.
I guess I'll ask one more, which is, so this seems like it really requires that you trust the authority that's forming the community. So it's like the honesty generator. Do you know, is there any hope for the, or actually, I guess one question is just, are there any results for lattice-based accumulators for the setting where you don't trust, where it's sort of like a commitment, like a binding?
Yeah, actually the prior construction that I mentioned during the the experiment phase where I had the table with the numbers, yes, the ones at the top, I can quickly go back to it. Yeah, so these ones at the top, well, this one at the top here, yes, it's fully transparent, right? Like everything, the generation of the public parameters is transparent, and additions and deletions are also transparent, so anybody can add and delete.
I see.
Yeah, but the thing that you lose there is that when you perform addition and deletions, you need to update the accumulator value and also update the weaknesses.
I see. Yeah.
Yeah. But also overall, like in order to kind of like circumvent this requirement of changing the accumulator value during addition, similar, you will need this trapdoor, right? Otherwise, anybody will be able to generate the weaknesses since the accumulator value does not change in some sense. Yeah.
Any other questions? Thank you.
Thank you.